Before we do some, we need to go back to an example that we left unfinished last class, if you recall. But before we do that, I would like to just go over a quick review of the new material that was presented last class, just to bring everything fresh in your minds. And so basically we presented 3 of the 4 basic principles that we're going to use in this section of the lectures, which is on fluid dynamics. And well, it's kind of the heart of the applied engineering fluid mechanics, these principles that we're discussing now. So it is important, it is very important that we get comfortable with these principles. Conservation of mass, in the first place, or otherwise known as continuity. When we talk about continuity, it's just conservation of mass. It's another name for the same thing. And basically we know that in the absence of nuclear reactions, which we ignore in the context of this course, mass is not created nor destroyed. So the change in mass for any control volume has to be equal to the balance of what comes in and what goes out in mass. So we have the sum of any fluxes that go in minus any fluxes that go out. That is the simplest form of the conservation of mass, where the mass flow rate, m dot, we usually can use a very simplified expression for that, which is rho AV for uniform velocity, which many times we can assume using perhaps an average value of the velocity if it's a pipe or something like that. And in the case of the very special case that many times we can apply of 1D steady flow, such as again in a pipe, then we simply have the expression of conservation of mass as rho AV equals, to a constant. I didn't mean 0, I mean a constant. The simplest expression of conservation of mass, and many times we can use that like in this form. So for those of you that have bought the textbook for this course, let me just note that you can look at additional examples there on pages 85 to 91 for steady flow, and pages 91 to 93 for transient flow. Okay, additional examples. I am not taking the examples from the textbook, but giving you other different examples so you'll have a greater variety available to you for practice and study. Okay? That's conservation of mass. Conservation of momentum was the next one. So I'll wait for a couple of you who are taking notes of that, and so far this little review. Okay? And conservation of momentum. Again, we write the simplified version for 1D steady flow, which we will often use, which will often be sufficient. And in the case of conservation of momentum, the equation is rho, say, for a section 2, the area of that section 2 and the velocity of that section squared, minus rho A1 for the section 1, say, in a pipe, has to be equal to the force when we're just looking at one-dimensional flow. So everything is just, say, the x direction. We don't have to worry about directions. In general, that is the simple case for, say, a pipe with a change in area. The simplest possible case that we could have. But in general, the general form of the equation is an integral equation, where an integral vector equation, in fact, where the sum of forces as a vector is equal to the change with respect to time of the momentum in a control volume, v velocity, rho dv, when this guy is volume, so I put a little bar there to indicate it's a differential of volume, plus the integral across any control surface of velocity, rho, and then we have this dot product of velocity and the normal, unit normal, and an element of area. This is the most general form, but we know that many times it will simplify. It looks a little bit daunting, but the way it simplifies, many times the situation is steady, so this guy is equal to 0. And of course, if we choose, for example, the control volume wisely, such that this dot product here, for example, if the velocity is always perpendicular to the control surface, and we are free to choose the control volume in that way, then this simplifies quite a bit, and we don't have to worry about those integrals and so on. So what do these two integrals mean? This represents the time rate of change of the momentum in the control volume, right? We have the time rate of change here. And this other integral represents the flux. The flux of the net flux of momentum across control surfaces. So that's the interpretation. That's what those two integrals represent. And we're saying the time rate of change of momentum in the control volume plus the net flux has to be equal to any force that is being applied to the control volume. The types of forces that we can have, we discussed also last class. The types of forces that this could include were pressure forces, the weight, viscous forces or forces due to shear stress, and also forces that are related to interaction with any bodies, any objects that are in contact with the flow. So it could be an immersed body, for example, if we have, something flying in an immersed body, or it could be something surrounding the object, like the pipe system itself. So any interactions with objects can, of course, generate forces. Those are the types of forces. And so again, let me tell you that if you want to see more additional examples in the textbook, these can be found in pages 97 through 102. Additional examples for conservation of momentum available there in the textbook. That was, yes, question?
What do we mean by control surface?
The control surface is just the envelope of the control volume. The control volume is a volume that you decide to use for the purposes of the analysis of a fluid system. And when we do more examples, it will become more natural to you. We saw last time one example, which was the rocket, and we simply decided to draw a box around that rocket, right? And that was our control volume. And the strength, or the strength of that analysis system is that everything that happens inside the control volume that we've decided to use for the analysis is completely a black box. You don't care what's happening inside. What you care is what comes in, what comes out, and you make you use this analysis to determine any forces that are applied to this control volume using change of momentum. Any changes in mass would represent accumulation or depletion of the mass inside the control volume because of unbalanced fluxes and so on. So we use it as a abstraction of the system that we're studying for the purposes of analysis to apply these principles in the most convenient form for engineering analysis. And with more examples, this will become more natural to you. So we'll continue doing some more examples immediately. Any more questions? These were the two basic principles that we presented last class. I wanted to make sure to remind you. And the third one was the Bernoulli equation. We'll discuss much more about the Bernoulli equation, different forms that it can take, different interpretations, the assumptions that are being made, and what are the limitations, and so on. We'll discuss a lot more about that. But let me just remind you the form of the Bernoulli equation for the simplest case that we saw, which was the case of one inlet, one outlet in our system. P1 plus 1/2 rho V1 squared plus rho G Z1 equal to the same quantities but at the outlet of our system, our fluid system. So 1/2 rho V2 squared plus rho G Z2. This was the form that we presented last class. And as I said, I will justify this increasingly as we get more used to it. So let's go back to the example that we were working through at the end of last class. I will remind you more or less how far we had gone without repeating the whole process. I will just remind you where we were, and then we'll finish it. So first we did the rocket example, and our second type of application for these principles was what I generally called nozzles. In this case, it was a nozzle that was fixed to a particular system, fixed to the planet Earth through what are called flanges. So if I quickly go back to here, this presentation, this title slide here, and to show you this photograph, these plates are what typically we call flanges, just simply some plates that we use bolts to fix together different piping fittings. This is what we're talking about. And here the flanges are holding together this contraction of the piping system so that the fluid accelerates and comes out in the form of a jet. So in this case, the trick was to draw, the question of this problem was to find the forces at the flanges, okay? And the trick was to draw our control volume, which is this dashed red line, in such a way that there was, the control surface here is passing through the exit of the nozzle. So I know that at this point there's a free jet. A free jet, the word free should tell you that it's just at atmospheric conditions. So I can know that this is atmospheric pressure here. So if this I'm going to call my section 1 and section 2, I know that the pressure at section 2 is atmospheric. The pressure at section 1 was given, I believe, yes. So let me write down the data that was given for this problem. We were giving the diameter at section 1, it was 60 millimeters. The diameter at section 2 was 10 millimeters. Rho, the density 1.22 kilograms per meter cube. P1 gauge, already we were giving absolute pressure in this problem, but we'll just write it gauge now because we already calculated that. It's equals to 3.7 kilopascal. And we applied Bernoulli's equation and we said, simplifying things, P1 plus 1/2 rho V1 squared. Z1 is equal to Z2, so we drop that out in the equation immediately. And P2 is atmospheric, so P2 is 0 gauge. So I just have on the section 2, 1/2 rho V2 squared. So this was our Bernoulli equation for this situation, because Z1 equal to Z2 and P2 equal to 0. Then we use continuity, and we had V1A1 is equal to V2A2. With these two equations, we were able to find V2 and V1, and that's where we left off at the end of last class. We found V2 is equal to 77.9 meters per second, and V1 is equal to 2.16. I didn't actually calculate it, but I told you that was the next step, and that was where we left off last class. Everybody with me? I don't know if everyone was there, but this is what we did last class, and I hope now I've all actually caught up with putting the class videos on iTunes, and so up to this point you should have, if you missed a class, a lecture, or for whatever reason, you should be able to catch up because it's all there available to you. So I said at the end of last class we're not finished, and we're not finished because the problem required us to find the force. The force basically at the flanges. This force is unknown. This is our engineering question that we want to know, for example, to calculate how many bolts are required to hold this in place, and so on. To be able to mechanically design the system, we need to know the force. The other force working on the control volume is of course the pressure, P1A1 applied here. P2A2 is 0 because we're working with gauge pressure. That's the advantage of using gauge pressure for such a system, and also the advantage of choosing your control surface wisely by crossing here the jet at the point where it's at atmospheric pressure. Make sense? Yes? Okay. So P2 is equal to 0. Are you guys following me? Yeah? Okay. Just to make sure. Okay. Oh, yeah.
When you're using the area as the surface of the edge of the control volume, you're neglecting the fact that there's any differential across the jet or anything like that, any like the parabolic.
We are considering, of course, the case of uniform velocity. Yes, we are assuming uniform velocity at each section. Basically, this velocity here is an average velocity. So to finish now, we need to apply the conservation of momentum. Okay. And in this case, everything points in the x direction, so we don't have to worry about a vector equation. We just have the x direction. And so the sum of forces in the x direction has to be equal to the change in momentum. The sum of forces in the x direction is F. If I look at all my control volume and look at all the forces, the only things I have are F and P1A1. Those are the only forces, the red ones. F plus P1A1, and that has to equal to the change in momentum. The change in momentum was the sum of m dot v out minus sum m dot v in. That's the momentum flux across the control surfaces. In this case, because we have all velocities perpendicular to our control volume, and we assume uniform velocity, like Nathan just said, and therefore that the integral across control surfaces simplify quite a lot, and we just have sum of momentum in minus sum of momentum out. The signs come about because we keep track of the sign comes from the dot product between the velocity and the normal vector. So in the momentum going in, we have velocity pointing in, yet the outward normal is pointing out, and so that's a minus sign. And on the other side, on section 2, we have velocity and the outward facing normal in the same direction, so that's a positive sign here. Make sense to everyone? Good. So that now we can write this as very simply as rho A1 V1 times, so this is m dot, and I've simplified things by writing m dot in the same form for both terms, and I have V2 minus V1. So rho A1 V1 is m dot V2 is the momentum going out, and m dot V1 is the momentum coming in. Now basically I can put everything in, all numeric values are available to me now to calculate f. If I take this term to the other side, f is going to be equal to, and let me take these terms first. We have 1.22 kilograms per cubic meter times A1, so that's pi fourth, and A1 is 0.06 in meters, the diameter, so that's d squared, pi d squared over fourth, and the velocity is 216 meters per second there. Oh, yes, that's correct. And then we have V2 minus V1, so that's 77.9 meters per second minus 2.16 meters per second. And then I'm going to take this, of course, to the other side, and it's minus 3.7 kilopascal times A1 pi over 4, and again I have 0.06 meters and squared. So all of those values are now available, right? I can put all of those numbers in the calculator and obtain my result. I've done this ahead of time to save some time, and I get minus 9.9 Newton. The minus sign tells us that we've simply drawn the arrow pointing in the wrong direction in the first place. So that's all it means, right? The negative sign indicates that the force points in the opposite direction than what we drew in the sketch. That is the force on the control volume. So the force on the control volume goes in the minus x direction. Therefore, the force on the flanges goes in the opposite direction. So the force on the flanges is on the positive x direction. So this is force on control volume points in the negative x direction, and therefore the force on the flanges point in the positive x direction. And that completes our problem. Everyone clear up to there? Question?
You say force on control volume. You're saying that I guess the interpretation of that is force on control volume.
Because all of the analysis that we have applied so far is what we call control volume analysis. So we've said the force on the control volume is equal to the sum of forces on the control volume is equal to the flux in momentum. This is the equation that we have applied here, right? Sum of forces in the control volume equal to the change in momentum across this control volume. So we have pressure acting. We've drawn a volume that is this magic black box. And we've applied the equation of conservation of momentum for that box. That box is cutting through the flanges through the middle. All right, so basically the box has one side of the flanges in it and the other side out of it, right? So the only source for that force is the fact that there's bolts holding the flanges together, right? There's a force that on the control volume, on this box that I've drawn, that points in the negative direction, so that because this is not moving, there has to be an equal and opposite reaction on the outside world. And that's the force we're looking for. That's the force that's keeping those flanges together, the equal and opposite reaction.
So we're just taking a one-dimensional, one-dimensional force diagram of the outer side of that, you say that the momentum going this way equals the force going this way.
Yes, but it's I've taken all of the, of course, that's just the resultant. That force is the resultant that is acting on, you know, if I drew this in 3 dimensions, it would be this complete disk that has the many bolts, like in the picture, and I've just taken the resultant of that and calculated that. And then if I want to apply some mechanical design, I would have to be able to, you know, split that up into each bolt and so on. Yes?
How come you just only use the area of the inlet area? Why, when you do the sum of the mass out, how come you don't do A2, V2? Do you don't do rho A2, V2 minus rho A1?
Well, the answer to that is that if I had done that, the contribution to the change of momentum in all of the rest of this area, say all of this area here, would be 0 because the velocity across that part is 0. So the velocity is only not 0 here in this part of the area. It is 0 everywhere else. So when I'm doing the integral, all of the contribution of this other area is 0 because there's a v dot n, and v is 0 in this part. It is only non-zero in this section here. This the exit of the jet, and is only non-zero in the actual section of pipe that is feeding the nozzle. That's why. So here in this part, yes, that's correct. But basically, I'm using this over here at the same time because m dot 1 is equal to m dot 2 because of conservation of momentum. So rho A1 V1 is equal to rho A2 V2. M dot is equal to m dot everywhere. And I've used that to simplify my algebra a little bit. Is that clear? Yeah? This is simply m dot. So that's why I wrote it this way, m dot v. This is m dot v1, and this is, m dot v2 is what goes out, m dot v1 is what comes in, and m dot is the same in both cases because of conservation of mass. And it just makes it a little bit easier for the algebra. But you could have done it the other way if you wanted to. It would have been correct. Okay, so if there are no more questions, I'll go on to another example. Is that clear? Do you think you can repeat that in your homework or similar problems like this? Yeah? Okay. So the third type of problem that we have, typical types of problems that we have in this sort of analysis, are what we call vanes. Vanes are simply components, some mechanical component that we use to turn a fluid jet, which is many times the vane itself is also being turned by this exchange of momentum. So it is some sort of device used to turn a fluid jet. Now, for these type of problems, the basic tips that I can give you are to basically neglect elevation differences, because in the scheme of things, for normal situations, normal velocities, the fact that the jet enters and leaves with a little bit of a different elevation can be safely ignored. So ignore elevation difference, unless, of course, it doesn't make sense, okay? But in general, for vanes, what we call vanes, it's just a small little device that is impinged on by a fluid jet, and the elevation differences are tiny, so we can safely ignore that effect. Also, the vane is open to the atmosphere everywhere, so P is equal to a constant. Atmospheric pressure everywhere. And finally, well, if P is equal to a constant and there's no elevation difference, Z1 equal to Z2, P1 equal to P2, so on our Bernoulli equation, the only term that's left has velocity, and so these two things together imply that V is equal to a constant. So Bernoulli equation is trivially simplified in this case. And we, of course, are assuming that the fluid is inviscid and the density is constant in all of this. Otherwise, we couldn't apply Bernoulli's equation. So let's look at an example. Suppose we have some sort of, so this is going to be my vane, crooked, but nevertheless, and the vane is, fixed to the rest of the earth somewhere, and we have a fluid that comes in as a jet and is simply being turned by this vane. So it comes in horizontally there. That's supposed to, what I wanted to show is a little crooked, but it's horizontally coming in with V1 and outwards going out at 60 degrees with, well, V1 as well, because V velocity is constant. So this is just a water jet that is being deflected by 60 degrees, nothing more. And we want to find, of course, the force which is exerted by the jet on the vane. Let's put some numbers in here. So the incoming jet speed is 100 feet per second. We're going to use British units in this one. The jet diameter is equal to 1 inch. And we need to find the force. On the exerted by the jet on the vane. So now we have to probably go to the back of the book and get some properties. We're working on British units here, so the properties in British units are going to be rho is equal to 62. This is a water jet. .4 pounds mass divided by feet cubed, and by Bernoulli we have V1 equal V2, so V1 is constant, V is constant. This is immediate from our neglecting the elevation differences. Pressure is atmospheric everywhere, elevation differences are ignored, so V1 equals V2. And continuity Well, all the mass flows have to be equal, so we can just use m dot for mass flow. So the trick here is to choose a proper control volume. So let's choose a control volume wisely, and the wisest way to do this is to be always perpendicular to the velocity. So we're going to be perpendicular to the velocity at both places. In the middle, it doesn't really matter because the velocity is 0. So in between here, we don't care. But the surface at the entrance and the exit of the control volume is perpendicular to the velocity. So we have a resultant force here in the y direction and a resultant here in the x direction, both at the point where the vane is being kept fixed somehow. Let's call this Fy and Fx, the two forces. So there's only one total reaction force, but I've just written it in components. And we have a momentum flow. The momentum flow is simply m dot v entering here and m dot v at the exit. That's our momentum flow. Yes?
I said a little while ago, you said the control volume in like the middle section, like the way you choose it doesn't matter because the velocity is 0. That's it. What velocity is 0?
The velocity of the fluid. And so because there's no, the velocity of the fluid is 0 in this, across this surface, I don't really care the shape it has because I'm not going to have to worry about writing a contribution to that integral that is across the control surface that indicates the fluxes of momentum. I'm not going to use it in any way in the problem. So I draw it in a way that makes sense, but I'm not going to use it. That's all. But I am going to be worried about this here, this control surfaces, and this one over here, because there's some fluid going in and going out, and that's where momentum goes in and out the control volume. Okay? So far so good, everyone? Any other questions? Now we're in pretty good shape. We've selected the control volume, we've drawn the forces on the control volume, and we've drawn our momentum fluxes. Now we're ready to use this. We write our momentum equation. The only difference with the previous examples is that now we have to actually write the momentum equation in vector form. We have two components. We have vertical and horizontal contributions, and so we write the two components. So in vector form, I would write the sum of forces as a vector is equal to the sum of m dot v as a vector out minus m dot v as a vector in. So I have to write the momentum outflow vector basically as two components. So momentum outflow vector, I'm going to write the two components. We have a component in the x direction, which is, so this is 60 degrees. So if I multiply by the cosine of 6 degrees, I get the horizontal part of that, right? So it's m dot v cosine of theta times the unit vector in the x direction. In the y direction, we're going down, so it's a minus m dot v sine theta, sorry, yes, correct, sine theta, and unit vector in the y direction. So that's the vector form, so that of the outflow. the first component. And the momentum inflow in vector form, well, it's only in the x direction, so it's not hard. M dot V times the unit vector in the x direction I hat. And now I can write the force. Well, of course, the force vector also is the reaction in the x direction times I hat, and the reaction. I've drawn them both with negative signs, so I need to be careful of that only. So basically, I'm saying here the forces are F minus Fx in the I direction minus Fy in the j direction. I've drawn them with the pointing in this way, so I can now find those reactions. Everything relies on me using the mass flow rate. Mass flow rate m dot is equal to rho AV. But we know that we have rho, we have the area because we have the jet diameter. So that's all known. M dot equals rho AV. We have the diameter, we have velocity, we have rho, so all that is known. So basically now we can calculate the forces. We can do this component-wise, and I can do immediately minus Fx, that component is equal to, here's the, so I have to add everything that is going in the x direction. I have m dot v cosine theta, this term here, and plus, no, minus, because this is inflow is always with a minus sign from my equation here. Minus m dot v and minus fy in the y direction. I only have one contribution, which is the outflow contribution in the vertical direction, m dot v. Sine theta, sorry, forgot the sign here, from here. And everything is known. The momentum inflow
I don't understand the sign
is
between m dot v I hat and then momentum inflow vector. If you look at, and then that.
well, the momentum inflow vector points in the positive x direction as I've shown it here in my picture. But when I put that in the equation of conservation of momentum, it needs a minus sign because of the normal unit vector pointing in the opposite direction. So that's why I've put the minus sign here when I plug it into the momentum equation. So you now have seen that we've come to, be able to calculate all the forces, and I'm not going to go through the algebra of manipulating the numbers themselves, and I'll just give you the answer in terms of numeric values, and you can check this in your own time. 53 pounds force for the x direction, and the y direction is 91.8 pounds force. And that is, again, that is the force on the control volume. So that's sort of keeping the control volume in place. So we have to understand that the force there's an equal and opposite reaction basically on the outside world, which is going to be the force on that little beam or fixture that is keeping the vein in place. This is a very, very typical type of problem that you will have to solve. Yes? This, in red, is the force on the control volume, which I've drawn in this way. The answer is gave me a positive sign, so it means that the arrows that I drew are correct as the force in the control volume. And so the control volume is not moving, therefore there's an equal and opposite force on that little bar that is holding things in place, that is holding the vein in place. Like we did for the rocket. We had the same situation. So this, again, like I was saying, is the third type of typical problem that you'll have to solve. An example, this is like a standard example of problems you'll have to do. And I think it's a good place to take a little break, and we'll do the final type of problems coming back in 10 minutes.